Hey, I'm Sean. So memory is a super popular term in AI agent systems recently, and the reason for that is that any LLM call does not carry any weight for long terms. The reason why your ChatGPT and Claude Code remembers what you talked about from the past is because it has already crafted this memory system for their own AI agent harness. Today we're going to cover 5 different ways of how you're going to architect a AI agent memory around the harness you built. And previously, if you have watched our videos, we have created this agent harness called Waku agent. It basically has this agent run that has a loop for the agent to call tools, delegate sub-agents for tasks, and at the same time it's going to prepare this working memory with retrieving from 3 main pillars, which is procedural memories. In our case, it's a skill, semantic memory, which is some durable facts, and episodic memory, which is some dated events. And that was pretty much similar to how Hermes agents crafted their own memory system. But if you're serious about building agents, I'm sure you have been bombarded with information such as RAGs, agentic RAG, graph RAG, retrieval augmented generation has always been there. But there's no retrievals or embeddings in Hermes and Waku agent. We're going to tell you the difference between these 2 separate systems because they are 2 different ways of retrieving memories. And I hope this will be helpful for you because eventually it depends on you what kind of memory systems matters the most to your use case, and then you should make a decision by yourself. And if you want to try out all these agent harness and memory systems and everything, we have built an open source project called shanshongchen/waku-agent, and we recently received more than 1.3 thousand stars. So thanks everyone for your support, and we'd love to have you to contribute to this repo. And the way to use it is very simple. You can either pip install Waku agent, or you can git clone this repo and then start working on it. Once you start running it, you will have an agent like this, and you can ask it questions and be like, what is on my calendar today? If you have your calendar, properly set up, and it's going to pass through the retrieval gate and then, use the tools like list events to check out calendar and all these kind of stuff. So this is a proper agent harness that will allow you to play around with your memory system and tools that you build for yourself. After finishing the tracing and then giving us back the answers, we're pretty much done for one agent run. And we also built up this arena for memory systems to compare a few different memory layers options on the market. We're going to show you all the real code and implementations at the latter half of the video. For now, let's jump back to the system design for the concept explanations first. First things first, here's how I would think about agent memories. I would think about 3 main pillars first. What is it, how to find it, and how do we maintain it? Normally, an agent memory will be stored in 3 different ways. The first one is text or markdown file, just like your memory.MD. For example, if you come to Hermes and just ask any questions and say hi, and then you will see your root directory. And if you scroll down to .hermes right here, and then scroll down, you can find out that, and then you'll see a folder called memory, and then double click on this memory.md. It will show you the memories right here. Okay, so this is just plain text, and it's going to be fed into the context window whenever you ask any questions. And similarly in Waku agent, if you clone this repo, after you ask some first questions, you will be able to find this folder called .waku, and then you can find things like SOUL.MD, which is a system prompt for your AI agent memory. So basically it can be just in plain text. Or if things get more complicated, you can store them in a table, like a spreadsheet or like a Google sheet, with rows and columns, all these kind of stuff, just like an Excel sheet. And last but not least, we can also store information in a graph with nodes and edges. And for people who are not familiar with graphs, it's basically a way to build up connections between information. And I found this really cool tool called Zap, and they have this relational graph that after you use this memory layer to store information, it will plot this out for you. For example, let's take a look. Let's say this founder called Alex, and Alex has been to this Lisbon AI meetup event for his robotics startup, and you can see that these information are all interconnected. So it started with this username called QuickStartZap3, and then Alex similarly has a product launch date, and those were in, say, in May, they had a product launch. In June, also had a product launch. So graph is just a way to store information that helps you find connections between infos. And I think these are the 3 major ways of storing memories. But people might be asking, where's embedding for retrieval augmented generation? It depends on what vector stores you're using. If you're using Supabase PGVector, like myself, it's going to be still in rows in a table, but then some of the columns are going to be vectors, or you can store them in a NoSQL database. So that's what is it, right? And then now it comes to how does our agent find out about it? There are 4 ways for an AI agent to find the memories. The first one is do nothing. Remember the memory.MD that we showed you earlier for Hermes? That's basically do nothing, because if the memory.md is not too long, it's supposed to be read by default by the LLMs so that it's always in the context anyways. Remember, if you use Claude Code, you can see how much percentage of the context window have you used, and sometimes it's huge. And the reason is because some of the memories are just going to be preloaded there. And also, of course, there are a bunch of tool calls, definitions, MCP definitions, your SOUL.MD, which is the system prompt for the role that the agent is playing. Other than that, we can also do keyword, which is something that SQLite has, which is a standard called FTS5. All you need to know is basically it's doing keyword searching, okay? And an example in Hermes is that if you come to Hermes and you scroll down again in the same folder, there's something called state.db. And if you open that, you can see a SQLite schema here. All right, and the keyword search is basically given these state.db, we're just going to search the keywords of the information. And the third one is for retrieval augmented generation. It's something that it's basically checking the similarity between 2 words. Let's say you're asking a question regarding my favorite food, and the word food might be embedded into a vector of space 1024 by 1. And then it's going to just calculate what other words that are embedded in the same dimensions in our database have a high similarity to food. Maybe it's going to be apple, maybe it's going to be sausages, or so on and so forth. Okay, so what we're trying to do is doing a semantic search instead of just doing keywords. Last but not least is GraphRag. What GraphRag does is very simple. Remember I showed you about the graphs earlier? What it does is basically it's still embedding the information, but it embeds things like the nodes. Okay, maybe embed product launch date. And it also embed that edge, like is it part of the observation or is it a relationship? Okay, and all of these will be embeddings. The similarity search will just find out what's similar to the question that the user asked, and then eventually it might return a relationship graph here, so that the agent has more context about the memories in relationships. So now, how do we maintain it? I have summarized this into 4 main ways of maintaining a memory system. The first one is you got to make a decision, which is do we add, do we delete, do we overwrite some previous information, do we do nothing? Okay, this one means no operations. Or do we retire some information, which by the way is different from deleting because we're not deleting it. We're invalidating the previous information with some time range. What does that mean? We launched Waku Agent 1 month ago and it got 1,000 stars in the first 25 days. Okay. And then the next day, I'm telling the agent, today is day 26, and the Waku agent has got 1.3 thousand stars. So it increased 30% in just 1 day. And then what should happen is that instead of deleting the fact that this GitHub repo has gained 1,000 stars in 25 days, which is still important information, you can probably just invalidate it and be like, hey, the latest stars is 1.3 thousand already. And you can trace back to 1 day before, which is 1,000 stars. And these contexts are still important for future tracing purposes. The third one is called attribute, which in human language is that it's basically tracing where the source comes from. Okay, maybe I got the memory from the users communicating with your agent, or maybe I got it from some web search, or maybe I got it from some calendar search, right? Depends on where the source comes from. And last but not least, we are talking about reflect, which is it's going to drop or merge some of the duplicates or some of the outdated information. I mean, it's kind of similar to delete and kind of similar to retire, but reflect sometimes can link to what Anthropic has proposed, which is dreaming. Dreaming happens when we're not working. When the agent is running, it's like busy accumulating facts, accumulating episodic memories, accumulating procedures into skills. But then when it's not running, we can probably schedule some tasks to let it reflect on everything that we have collected and then merge some of the duplicates or drop some of the stuff that are not important anymore. So it's kind of like a post-mortem or post-process step to update or maintain the memory system. Are you guys still with me? Good, let's keep going. Now let's see some different types of memory systems with real products. And let me add the vector store here. So first thing first, plain text ways of storing memories. Examples are Hermes and Waku agent. I've shown you SOUL earlier, which is text, and it's basically a system prompt, and you can just edit it, right? If we check out the SOUL of Hermes, you can see that my Hermes has a personality, which is it should always talk like Pikachu. It should say Pikapi all the time. And there's some variations. You can say Pika or Pika Pika or Pikapi, right? And the Pikapi reserved for addressing me directly. Like you should call me as Pikapi, because in the anime, Pikachu also calls Satoshi or Ash Pikapi. And you can edit this to anything else, right? So it's very simple to understand. And skills is a procedure. For example, research about all AI agent videos on the internet, and then inform me every morning what are some of the latest news that Sean AI stories should cover for the next video, right? This is a procedure, this is a skill, and it's usually loaded by trigger, okay? So if I'm asking my agent, then be like, hey, trigger that skill for Sean AI posts, and then it should run it and then fetch it for me, and I should always be able to just edit it myself. Memory.MD, which is some durable facts that you should keep accumulating when you're talking to agents like these. This is from a previous video for showing you how to build agent harness in real code. And the way that we build up semantic memory, which is basically memories.md, is that every time when you have a conversation with the agent from the user prompt to the LLM, to the reply, it should save the history into the state.db, which is our SQLite database, and then it should consolidate the information after every, say 5 or 10 conversations using some cheaper auxiliary models, and then it should distill the facts into the memory.md. And these memories usually are loaded in context because that's important, but you can also make it retrievable. You can build up a retrieval gates like what we do in Waku agent, and you should decide if it should call up some skills, call up some semantic memories and stuff, right? It doesn't have to always be there, but you can do that if you want to. And remember, agent harness is very flexible. You don't have to stick to any standard. You can just craft your own harness. Eventually, what lasts forever, or what matters most to you eventually, is the memories. If you're accumulating these memories and then store them well and prepare them well and then take care of them, then these memories are the most valuable assets for any AI agent harness. Whether or not we should have a retrieval gate, that's completely up to you, okay? And last but not least, remember we just showed you the state.db, which is the SQLite database, and it's a relational database with roles, and you're doing the keyword searching for how to find it. And then the way we maintain it is that you can just edit it yourself. Like if you click on here, yeah, you can just write things into the state.db, or you can wait for the agent harness to consolidate it, like what I showed you in Waku agent, the consolidation. And in the real code, we also have a consolidation module right here. If you click into it, you can see what happened in consolidations in the past history. Okay, so that was plain text style. What else do we have? We've got Supabase, Weaviate, Pinecone, which have vector stores. Well, Supabase is a relational database, so it's technically not a vector store, but they do have a SQLite extension called PGVector, which is technically a vector store that you can use. Vector stores usually store information in vectors, which, as I mentioned earlier, is going to embed every single word into a high-dimensional vectors with numbers in it, because computers cannot process on words. They can only process numbers or higher dimensions of numbers. That's why vectors are very useful. And then you can store some metadata, for example, what does this vector really mean, and what some other information should be carried with it, okay? And the way we find it is that we're going to do this thing called similarity search. Remember earlier we said that we're going to put a high dimensional number vector on the word food, and then you're going to search, the space similarity, space distance between food and apple and sausages, and then grab those food that's in our storage, in our memories, okay? And the way we maintain it is that you basically just insert or delete information from it. But you can make it a little bit smarter, if you have a vector store in your agent harness, and you can just, design it in a similar way like our consolidation module I showed you earlier for state.db, but instead it's for vector stores. And now we're looking at some memory tools out there on the market. Meme0 is one of the interesting examples. They have two ways of storing memories. One is called row memory, another one is called graph memory. What a row memory does is that, I'll just show an example. This is a portal I'm in for meme0, and then they have a tab called memories. If I just click into one of them, and this one says we have a German buyer, and this German buyer requires vegan certifications on every SKU that they got sold for. This is basically just a semantic memory, like a durable fact that will last here forever. And if you have an agent and you can ask them questions, and it should pull information from the meme0 memory layer. I don't know if they did plain keyword search here or doing some embeddings or RAGs, because I mean, yes, they are open source, but this is an enterprise version, so I'm not sure which one they're actually using behind the scene. For role memory, the way you maintain it is very simple. You add, update, delete, or do nothing, or supersede it. Supersede is basically what we covered earlier, which is you don't delete the information, but you make the previous one go outdated. And you say, hey, we have 1.3 thousand stars for Waku agent now, not 1,000 stars anymore. But we do not want to delete the fact that it has 1,000 stars in the first 25 days. And meme0 also has graph memory. Graph, remember what we said? It's basically nodes and edges, and then it can store things in vectors. Row memory also is stored in vectors. Sorry, I forgot about that. Both of them store in vectors, and it's going to check traversal, which means you're going to check the entire graph for information. And also, it does add, update, delete, nuke. I'm not too sure if it does supersede. Maybe it does too. For these things, you should check the source code. Unfortunately, the graph feature for meme0 needs me to upgrade to their pro, which I'm not going to do, because I found an alternative tool called Zep. Remember this chart I showed you? This is their graph. So what Zep does is a memory called temporal graph memory, which means that this graph is evolving over time. Okay, it's got the nodes, got the edges, it's got the validity, which as they claim, the way you find these information is using vector search on nodes and edges and across the entire graph traversal. And the difference is that here it can invalidate with some time range, like superseding. It's like similar to superseding. You never delete it, but the history survives here. And if you check Zep, it's by default using graph. And you can check the previous batches of conversations, and you can check the threads, stuff like that. Okay, I will show you real examples of all of these memory layers in just a moment. Last but not least, we got lang chain memories, which is called LangMem. LangMem is just LangMem. Okay, there's no stores. It's basically a package that allows you to store locally, and it's your own stores search that you're using, and you're extracting and resolving, the store update before writing into anything into it. So this is kind of the high-level overview of memory layers for AI agent. As I explained earlier, you should pick the right one for your own agent harness, and you should take good care of it. For Waku agent, we're currently working on some more comprehensive memory layers, so please stay tuned. And if you're interested, please leave a comment or join our community. And if you want to participate in this or try the early versions of Waku memory agent layers, you can come to our community in seanchen.io. And here you'll be able to join our community where I'll be replying questions live every 2 weeks with our community, or you can just click into any of my social media to communicate with us. Now let's start testing things. Again, come to Waku Agent GitHub repo. You can either run this in your terminal to pip install, or you can just git clone it. UV run Waku dashboard will bring you to an agent harness visualization like this. In the arena section, we have built up this thing called memory arrays. And the way we deal with memory arrays is that we have a set of questions. For example, if I choose the dinner party with some facts and questions, and I zoom in a little bit, I can see that stuff I'm going to tell each one of these memory layers. And if you come to what they get asked, it's going to say what I'm going to tell each one of these memory layers. For example, Jensen Huang is coming, and last time he knocked my chili oil onto the right rug. And Elon Musk is coming too, and he said he would get here at 7 o'clock. And Tom Holland, the Spider-Man, is also on the list, and he told me the ending of his next film over coffee last Tuesday. Remember, Tom Holland can never keep the secrets of an unpublished film. That's basically the memory I want to tell to these memory layers. And there are some sample questions, right? If you ask about Jensen, it's going to say, okay, he basically knocked off my chili oil. If I ask a question related to how much does Paul Graham owe me in Chinese, Paul Graham owes me $20. All right, because here it says that he owes me 20 quid from sourdough we met in Lisbon. Quid is the way you say pounds in the UK because Paul Graham is British. Anyways, and at the bottom, you can see that we have listed a few memory stores, including SQLite, Meme0, LangMem, Zep, Control. I'm not doing Supabase yet because we're not testing embeddings here. If you're interested in RAGs and embeddings, please check out my previous videos on agentic RAGs and RAGs. They're all in this channel, so feel free to look them up. Okay, and I can click on Read Store to check the current memories. So it's pretty much empty for the current date because I have cleaned it up. The other memories you saw earlier were just some legacies from the previous iterations. So what I'm going to do now is that I'm going to click on Ask 5 Stores. If I scroll down, you can see that we are now telling these facts to each one of these memories, okay? With Control being the one that will just be, having no memories. And let's see if it actually works if we ask the same question to the control group. This is a seeding process. We're going to tell these facts to each one of these memory layers, and then later it's going to ask the questions and see how fast they respond. Okay, and because writing it takes some time, so I'll just leave this for a second and we can come back to this in a bit. I want to show you exactly how to use some of these memory layers in plain code. If you come to Waku Agent, and we can check out the folder called examples. Okay, we open examples and there's a folder called memory native, and here we have LangMem native, which is the LangChain memory. And if you scroll down to row 42, we have added some facts, like I met Alex at Lisbon AI meetup. Product launch is scheduled for May. Actually, the launch moved to June. Remember, this is superseding, like making the previous information, not deleting it, but it's basically outdated. And there's some questions. What is the product launch? What date did we push the ship date to? And 发布会是什么时候 in Chinese, so that we can see if it actually works. And then later you can see that we are creating this memory manager with this manager. And then for every fact, we're going to invoke a conversation. All right. Another example is Meme0 native. So if we click into it and scroll down a little bit, you can see that we have the same facts and questions. For Meme0, you need to create a memory client first. And then for every fact, we can do client add, which is writing the memory into Meme0. And then later you can test it with some real questions, with some searches. Okay. Similarly, we have a Supabase native here, exact the same process, but for Supabase, you need to do some embeddings. And later you're going to do retrievals using the embeddings. And last but not least, with Zep, we fed the same questions and facts again, and we have built up a client from Zep, and for every fact, it's slightly different here for Zep because it's by default a temporal graph memory. For every client, for every graph, you're going to add the fact, okay? And then it's going to build up the graph for you, okay? And then you can use the client.graph search to find out the results using this query, okay? Feel free to try this out. Okay, let's come back to here. We can see that except Zep, everybody else has finished the work. Let's see. So make it bigger. What did Jensen Huang knock onto my rug? And NVIDIA should be paying for this. It passed for each one of these memories, except Zep is still taking time to build the graph. I have no idea, but I feel it's because that building the graph takes time. Okay, maybe that's why. And it took 4.6 seconds for SQLite. And the answer is correct. Jensen knocked chili oil onto the white rug. And Meme0 just said chili oil very fast. Very, very straightforward, but took a slightly longer time than SQLite. And the LangChain LangMem took the longest time, 7.5 seconds. Zep is still seeding, which is taking forever. And the control group obviously have no information about this, which the answer is correct because it should not. I don't have any record of that. That's right. And when I asked the question, how much did Paul Graham owe me, which is supposed to be 20 quid, SQLite answered it correctly. In English, it took it 10.3 seconds. I don't know, maybe because SQLite is a little bit too simple for keyword searching, so it doesn't really know how to search in Chinese because the memory was in English. But it seems like Meme0 got it, and then it said, reply to me in Chinese. It said, Paul Graham still owes me 20 pounds. And he lost it when he was betting with me in bread store in Lisbon. That's right. And LangMem also has a correct answer, and the control group also doesn't have anything. And when did Elon arrive here? It's supposed to be 9 p.m. instead of 7 p.m. Why is that? Because we have an update. You see, update on Elon. He can't get here until 9 p.m. instead of 7 p.m. So we're doing a bit of a overwriting or superseding, right? Because maybe I don't think this is overwriting. This is superseding because it's supposed to keep the previous information but make it, kind of outdated. And if you scroll down, you can see that all three of them answered correctly. And my control group says there's no events on the calendar with Elon. So it searched the memory and used some tools to check the calendar. It didn't happen. Okay, cool guys. If I click on read stores again, you can see that SQLite mem0 and Zep also has some memories already. LangMem has nothing because it's a package. Control group is control group. If you click on see all, you can see all of the memories. So you should also be able to find them in each one of these platforms. If you come to memories, you can see a lot of them. Okay, this was the stuff we ran 6 minutes ago for these durable facts. And for Zep, we should be able to see them too. Let's see. It's very unintuitive on Zep. What exactly is happening? I don't know where to find them, to be honest. Okay, I think in users, every time when I do an agent run, it's creating a new user. So maybe I should click on this new one and view the graph. Okay, good. It's from Waku Agent Arena, and it knows the sourdough bet. All right, program owes me 20 quid, and it was in Lisbon. Okay, good. And Elon basically knocked off the chili oil onto my white rock. You see, it's building the graph, which is pretty cool, but it took some really long time. Jesus, it's still seeding it. Oh my God. Yeah, maybe saving data using temporal graph is a pain because it's being delayed for so long. But I think this relationship with graphs, nodes, and edges probably still worth it. While we're still waiting for Zep, let's take a look at my main website, seanchen.io, and every 2 weeks I will be hosting a live session on this Warp community. And if you join us, I will be able to answer your questions live in our Discord channel. In our previous session, people asked me questions regarding all of our system design, and they have some implementation or deployment questions regarding, Waku agent and Hermes agent, Pi agent. If you're interested in having a conversation with us, come join us. Thanks. Back to Zep. Now it's asking the questions, finally. Waiting. Okay, let's come to Zep and check again about its graph. View the graph. Tom Holland is here. His next film. Oh, you see this edge carries information because Tom Holland and his next film, it means nothing. But look at this edge. This edge is saying revealed ending of. So Tom Holland revealed the ending of his next movie. So it did some summarization for me. Okay. And then program is node, and program owes me 20 quid. And he owes Waku Agent Arena, which I don't understand. But here there is, dropped on, somebody dropped the chili oil onto my white rug. All right. Not entirely sure, the chili oil stained the white rug, but it didn't say Elon. I'm not entirely sure this is doing its job. All right. But I don't know. It looks kind of smart that it built this graph, but yeah, I feel like it lost some information here, and it's taking forever. Maybe it's an overkill for a lot of these smaller use cases, which is why I think that Hermes and Pi agent all try to make things very simple, and it will just make things easier for everyone to get started with, and it doesn't take that much time. Okay, I kind of lost my patience. Whoa, finally. Finished asking the questions. Jensen dropped the chili oil. Okay, now it's finally asking the question. Previously it was just all waiting, you see. 4.9 seconds, 4.9 seconds, 6.4 seconds. Okay, Zep is taking forever. I think I have lost patience for it. I'll just keep it that way. Zep team, if you're watching this, I think this is a big pain point. Love your product, love your visualization, but please fix speed. Or at least do something about it for making simpler tasks faster. Cool guys, so this is a quick summary of 5 different ways of how we can craft agent memories for our AI agent harness. And I hope this is helpful. If you have any questions, feel free to leave us a comment and join our community and give us a star on GitHub and try out our Waku agent for your own implementation. Thank you very much. I will see you next time. Thanks.